Hello friends, this video on DNF block elements part 17 is brought to you by examfear.com. No more fear from exam. The next topic is the oxidation state, very critical topic. See, oxidation state actually determines the ability of atom to lose electrons to form compounds. For example, I have copper. Copper typically lose 2 electrons to form Cu2 plus, and this can actually form compound with, for example, Cu2Cl2. Right? It can form compound with chlorine, or sometimes you will see that copper forms compound with oxygen. Here also oxidation state of copper is +2. Correct? So technically, if you see d orbital has 10 electrons, okay, and s has 2, so typically it can exhibit up to 12 oxidation state. But for example, in this case, d has scandium, d has 1 electron, this has 2, 3, 4, 5, 6, 7, 8, 9, 10. These are my d electrons. Correct? So in this case, 1 plus 2, 2 is for s. S always has 2 electrons. We have seen the electronic configuration. For example, for scandium, it is Ar 3d1 4s2. This always has 2 electrons. So 1 plus 2 is maximum, it can exhibit 3 oxidation state. This is 2, 2 plus 2, a maximum 4. 3, 3 plus 2, maximum 5 oxidation state. 4, 4 plus 2, maximum 6 oxidation state. 5, 5 plus 2, maximum 7 oxidation state. 6, 6 plus 2, technically it should be 8 oxidation state, but it doesn't exhibit 8 oxidation state because losing 8 electrons is a big deal. It's not an easy task. This also 7 plus 9, technically it should have +9 oxidation state, plus again losing 9 electron is not an easy task. So the maximum oxidation state is +7. Okay, so as I'm telling you, it's maximum, technically it can have 10 plus 2, 12 oxidation state, but that will impact the stability of the whole atom. Okay, so the stability of the oxidation state of this transition metal actually depends on the nature of other groups attached to it. We'll talk about that. So depending on whether it is chlorine or fluorine, it also determines the oxidation state of this transition metal. Okay, and so the oxidation state actually depends on 2 factors. One is, we know that depending on the element attached. The second is the transition element, which gives the maximum number of oxidation state that occurs technically or typically in the middle of the series. If you see here, the maximum is +7, then again it decreases +6, +4, +2. Okay, from +3 it becomes +7, and again it decreases in this direction. Okay, why? Because the unpaired electrons are eager, they are unstable, and they are eager to form bond with other chemicals. Okay, therefore oxidation state will be highest in the very middle. Why? Because the unpaired number of electrons is maximum. If we talk about the unpaired electron here, let's suppose unpaired electron, this has 1, 2, 3, 4, this has 5, this has 4, this has 3, this has 2, this has 1, this has 0. Correct? So if you see, the unpaired number of electron increase and then decrease. This is the unpaired number of electron which actually determines the number of bond it can form, because you typically form bond with the unpaired electrons, right? And also the multiple oxidation state. If you see here, we have most of these has a multiple oxidation state, and the reason for the multiple oxidation state is typically small second and third ionization energy. The second and third ionization energy is not that much, so it is little easy to ionize these atoms. And note here, this scandium, it does not exhibit variable oxidation state. Scandium is always +3. Other transition metals, you see, all of these has variable oxidation state. Please understand this. This is a good question actually for exams. Which is the only transition metal which has only one oxidation state? Scandium is the answer. Scandium is the only transition metals which has only one oxidation state. Other transition metals exhibit various oxidation state, right? And also, as I told, the oxidation state actually depends on the ligands or the elements attached. So typically it has been seen that the fluorides, oxides, they exhibit higher oxidation state. In fact, the transition metal exhibit higher oxidation state with fluorides and oxides. Why? Because fluorides and oxides are typically very electronegative elements and they can easily attract electron toward itself, and it develops high positive charge here. That means you have higher oxidation state here. These fluorine and oxygen, smaller in size and highly electronegative, and with thus when the transition metal is attached to the fluorine or oxygen, it has higher oxidation state. We will talk about this later once again. Okay. So when you talk about the variable oxidation state, please note that transition metals are not the only metals or not the only elements which show variable oxidation state. We have, for example, sulfur, nitrogen, chlorine, oxygen, all these we have studied. They also show variable oxidation state. But their variability is less common in non-transition metals. In fact, lead and tin are the only two non-transition metal which has variable oxidation state common. For others, the variable oxidation state is a little rare. If you see, the dark one is the common oxidation state, and these in case of transition metals we have seen that these are very common. For example, iron +2 and +3 both are very common. But if you talk about oxygen is generally -2. Okay, chlorine is maximum time -1. But we have seen examples where chlorine is 0 also and -2 also. So understand, variability of oxidation state is not the proprietary of transition metal, but yeah, the variability is less common in non-transition metal. Okay, and now notice one thing. I'm telling that iron exists as Fe2 plus generally, or Fe3 plus, or you take any of these metals, they exist as they exist in this oxidation state. Now my question is, if I have iron solid, to convert this into Fe2 plus, let's suppose you have to first atomize it, you have to make it gas, and then you have to remove one electron, first ionization, you'll get Fe plus, and then again remove one more electron, you'll get Fe2 plus. Now for all these energies required, but still I say that this is more stable. Why? From iron solid you have to provide an energy here, then you have to provide first ionization energy, and then you have to provide second ionization energy, and then you get iron 2 plus. But still I see this is more stable. Why? Because see, energy is released. Why? Because this, when it formed, let's suppose FeCl2 or any compound with plus oxidation state, the lattice enthalpy or hydration enthalpy in case of liquid. So let's suppose it forms solid compound, then you talk about the lattice enthalpy. If you talk about a liquid compound with iron, where iron is +2 oxidation state, we talk about hydration enthalpy. So let's assume lattice enthalpy now in case of solid. So this lattice enthalpy, there is the energy released once the lattice is formed. Because the lattice is formed, the energy is lowered. It is more stable. Energy is lowered somewhere, the energy has to be released. The energy is released, and that energy actually compensates for all these energy required. Okay. Now, the more plus charge, for example, now Fe2 to Fe3 plus, again you need remove one electron, you have to again supply some energy, right? So in this case, the higher is the charge on transition metal, the more is the energy required to remove, because for Fe2 plus only 1, 2, 3 energy is required. For Fe3 plus, this third IE is also required. Extra energy is required now, right? More is the energy required, but this more energy is actually compensated by higher energy release. So maybe in this case you release more, higher lattice energy is released. In this case, little lesser lattice energy is decreased. So the point I'm trying to say is the lattice energy actually compensates for all these atomization energy, ionization energy required to convert a typical metal from a solid state to ion state. And if you see here, for example, I have iron, FeCl2, it is very easy to convert into FeCl3 from +2 to +3. But for example, I have CaCl2 is a non-transition metal. To convert to CaCl3 is very difficult. and this is easy. Thus, technically Ca plus 3 also exists, but these are rare. But in this case, it is easy to convert from FeCl2 to FeCl3. Both exist actually in nature. Okay. So now we'll talk about the oxidation states of iron. In fact, this is exactly what we'll be discussing just now. From FeCl2 to FeCl3 is easy. Why? Because if you see, third ionization energy is only 2960. And if you talk about CaCl2 to CaCl3, it is difficult. Why? Because third ionization energy is 4940. So this needs 4940 kilojoule of energy, and this is 2960 kilojoule of energy. Okay. This much kilojoule per mole actually.
Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.